You now know all about industrial control basics, cyber threat landscape, and the value of industrial frameworks. Let's now proceed to Module 4, Best Practices for ICS Decision Makers. By the end of this module, you will be able to explain defense in depth, explain the foundational controls of ICS, list the 5 foundational controls, and identify the different types of monitoring. Defense in depth is a notion derived from medieval European castles, where many lines of defense were employed to protect the castle from intruders. The moat, bridges, gates, inner and outer walls armed with cannons and soldiers, and tower keeps were among these tiers. The similar method can be applied to network security. It's a multi-tiered approach to network defense that requires numerous layers to be compromised before a cyber attack can do its maximum damage. Based on the layered defense technique, the defense in depth strategy makes it more difficult to reach the intended end goal while also adding the capability of detecting and stopping the spread of an assault. In order to detect and subsequently stop intruders from migrating from one part of your ICS to another or lingering on your network undetected, built-in redundancies are implemented. How does defense in depth look in an ICS environment? Consider the following scenario. Your cloud network connects to your plants, substations, and field facilities via edge network firewalls. Your plants and field facilities are then connected to a second deep packet inspection device firewall, which links to your PLCs. This is an example of network segmentation, which we'll look at more later in this module. Done by defense in depth, the attacker would have to get past multiple layers of security protections to accomplish their objectives. Let us look at each element of defense in depth. Risk Management Program. Identify threats, characterize risk, and maintain asset inventory. Cybersecurity Architecture. Standards or recommendations, policy and procedures. Physical security. Field electronics lockdown, control center access controls, and remote site video access controls, barriers. ICS Network Architecture. Common Architectural Zone, Demilitarized Zones, DMZ, and Virtual LANs. ICS Network Perimeter Security. Firewall or one-way diodes, remote access and authentication, and jump servers or hosts. Host Security. Patch and Vulnerability Management, field devices, and virtual machines. Security Monitoring. Intrusion detection services, security audit logging, and security incident and event monitoring. Vendor management. Supply chain management, managed services or outsourcing, and leveraging cloud services. The human element. Policies, procedures, and training and awareness. The basic cybersecurity procedures, such as network segmentation, vulnerability management, configuration management, and change control that serve as the foundation of a successful cybersecurity program are known as foundational controls. After you've got the fundamental security controls in place, you may go on to the more complex security controls. To minimize the greatest amount of risk and get the most bang for your security buck, you must first ensure that foundational controls are in place and that supporting processes are followed. Hardware and software inventories, change control, configuration log management, vulnerability management, network zones and segmentation are all foundational controls. The ICS cybersecurity best practices on which you should base your industrial cybersecurity program are these foundational controls. All of the industrial cybersecurity frameworks mention these controls. Let us learn more about foundational controls by looking at each of them one by one. Hardware and software inventories. Knowing what's in the environment goes without saying, yet it's one of the most basic stages towards safeguarding it. How do you protect something you don't know about? If you don't already have one, your first goal should be to create an accurate asset inventory that includes both hardware and software. It's vital for your cybersecurity program to keep track of this inventory over time. Your automation system's technology capabilities, as well as the threats aimed at them, will continue to evolve. This inventory is the backbone of your cybersecurity program, allowing you to deploy the other basic controls for those assets efficiently. Using a program that passively collects data on every connected device within your ICS is one easy method to acquire a high-fidelity level of inventory. This same tool can not only tell you what's on your network, but it can also establish a baseline for typical network communication, including the industrial protocol, so you can see if there are any deviations from the baseline and pinpoint deviations from normal operations. You can start to watch for and manage changes in your process configuration once you've established a baseline monitoring process. Someone in charge of an oil refinery, for example, may be aware that the system that keeps oil temperatures stable is their most vulnerable asset. An internet-connected device is used by a hacker to gain access to an email server. How do they get from the email server to the person they're trying to reach? The hacker must take a trail from IT to OT to reach their target, using crackable, weak equipment as stepping stones. That's why ICS operators require a detailed network map that shows the setup and vulnerabilities of each device. You can use this data to ensure that a conduit is in place to prevent hackers from accessing your most sensitive zones and assets. Change control. Not only should your process specify how to document, authorize, test, and deploy changes, but it should also map every change, from a firewall or switch configuration to a new control program uploaded to a PLC. Because all control engineers will know their activity is tracked against permitted work orders or change management requests, a change management process will be most effective if it is enforced with a detective control that emphasizes all changes. Plant operations systems can be crippled by unauthorized configuration modifications or approved changes made to the wrong devices, whether by accident or on purpose. These scenarios result in unscheduled effort to fix outages, which can be costly in terms of production downtime and quality recalls. Changes in configuration can also compromise a device's hardened configuration against a framework like ICS 62443, making it exposed to malware and malicious behavior, which can swiftly inflict damage on your ICS. For example, enabling a USB port while the framework requires that all USB ports be disabled. Understanding how configuration changes affect a device's secure configuration state is crucial for limiting the attack surface for malicious activity. Centralized log management. The way a data historian gathers and replays process events and sensor measurements for industrial operations is synonymous with log management solutions. The act of combining log information from all devices in your ICS into a centralized log repository is known as log management. These logs show the state and operation of the ICS's cybersecurity. Network equipment, switches, routers, firewalls, and so on, operating systems like Windows and Linux, applications like SCADA and HMI, and controllers and DCS all output logs. Log information is also provided by remote access solutions, VPNs, and authentication systems such as Active Directory. This raw log data offers a variety of information about how the system or device is performing, such as indicating a power supply failure or flagging cybersecurity events like failed login attempts. It's crucial not to dismiss this information, since it can serve as a type of predictive maintenance, highlighting potential downtime and unnecessary labor. Vulnerability management. Vulnerability management, VM, is the process of determining which publicly known flaws or weaknesses, also known as common vulnerabilities and exposures, are present on your network, CVEs. The majority of ransomware and malware assaults are the result of known CVEs that go unpatched or unremediated before the attacker strikes. Most legacy ICS equipment can't manage the questioning of vulnerability tests from typical VM scanning methods, which is a challenge while integrating VM in OT systems. There will be assets that are not suited for active scanning approaches as you get closer to levels 0 and 1 from corporate networks at levels 4 and 5. Devices in levels 2, 3, and 3.5 DMZ that are based on traditional IT technology, such as HMIs, data historians, and engineering workstations, are potentially better candidates for active scanning. ICS assets will benefit from an in-depth vulnerability scan from a VM tool as long as you know where they are. VM tools assign a risk ranking to vulnerabilities, allowing you to prioritize which ones to fix first. Network zones and segmentation. Network segmentation is accomplished by splitting your network into zones, which are organized by groups of systems that perform the same operational function and have the same risk profile. All communication in and out of the zone is blocked unless it is specifically approved through the use of firewalls or access control lists, which are created by a conduit. If a device, such as an HMI, is infected with ransomware, it can only harm other devices with comparable functions inside the same zone, because the conduit prevents the virus from spreading between zones. This is an important step in developing your defense in-depth plan. The ICS 62443 ICS security standard advises adopting the zones and conduits technique for network segmentation. Let us now learn a little more on the zones and conduit strategies employed in the network segmentation. Zone is a collection of logical or physical assets with similar security requirements based on variables such as criticality and impact. Conduit defines the boundaries of the zones and prohibits all communication in and out of the zones unless it is explicitly permitted. Effectively, a network pathway between zones in which applied controls can protect network traffic from network-based attacks, shield other network systems, and resist network-based attacks. Let us now understand the various forms of network monitoring. Passive versus active scanning. Passive scanning is required in some sections of your network to avoid interrupting sensitive legacy systems. The technique of passive scanning involves listening to network traffic and fingerprinting devices as they are discovered. This aids in the creation of an asset inventory, determining communication patterns, network mapping, and the detection of vulnerabilities. However, passive scanning can have some limitations. For example, network switches may not have the available port capacity to be the aggregator port for mirroring. Another limitation includes the performance capacity of the switch, as it may not have the processing power to perform mirroring as it requires additional processing overhead. Due diligence must be conducted to ensure that the switch fabric can support mirroring in order to meet the data collection requirements for cybersecurity and asset inventory. Active scanning or querying and polling can engage directly with a specific device to obtain extra additional data. The most reliable data comes from combining active and passive monitoring. Agent versus agentless monitoring. You must also know where and when not to deploy agents for data collection, in addition to passive versus active scanning. While agents give comprehensive information because they are placed locally on the device, check with your automation provider first to see if third-party agents can be installed on their HMIs or engineering workstations. You can also harvest data from devices via agentless scanning if you can acquire authenticated access. There are a variety of ways to collect data without using an agent, so choose the one that offers the most flexibility across both OT and IT protocols. A strategic balance of agentless and agent-based scanning is your best bet. Don't be discouraged by the amount of effort required to deploy all 5 of these foundational network controls. Everyone has to start somewhere, and for most people, that somewhere is acquiring insight into your network's devices, their communication patterns, vulnerability posture, configuration state, and log information. Here is a quick recap of what we covered. The approach for securing your networks is called defense in depth. Based on the layered defense method, this tactic is used to detect and prevent the propagation of an attack. Foundational controls are the fundamental cybersecurity procedures that serve as the foundation of a successful cybersecurity program, such as network segmentation, vulnerability management, configuration management, and change control. Passive scanning is a technique that involves listening in on network traffic and fingerprinting devices as they are discovered. Active scanning, querying, or polling can engage directly with a device to obtain further information. Since agents are installed locally on the device, they supply a wealth of information. You can also collect data from devices via agentless scanning if you can acquire authenticated access.